What connects a coin flip, a dice roll, and the number of car accidents in a day? They're all described by discrete random variables, the mathematical language that turns uncertain outcomes into computable numbers. Let's break it down. A random variable is not really a variable. It's a function that maps every outcome in a sample space to a real number. Flip a coin, heads maps to 1, tails maps to 0, roll a die, the outcome is already a number. That mapping function is the random variable. Think of it this way. The sample space omega contains abstract outcomes, and x assigns each one a number. X of heads equals 1, x of tails equals 0. The notation is x from omega to the real numbers. It's a function, not a variable. What makes it discrete? The possible values can be listed one by one. A coin toss gives you the finite set 0 and 1. A die roll gives 1 through 6. Daily traffic accidents can be 0, 1, 2, 3, and so on forever. That's countably infinite. You can pair every value with a natural number. If you can list the outcomes, it's discrete. The probability mass function, or PMF, is the core tool. It tells you the probability of each specific value. For a fair die, P of k equals 1/6 for every k from 1 to 6. Each bar you see represents a probability. Two rules define every valid PMF. First, every probability must be non-negative. Second, all probabilities must sum to exactly 1. These aren't just properties, they're the defining conditions. If a function satisfies both, it's a legitimate PMF. The cumulative distribution function gives you the probability that x is less than or equal to some value x. For discrete variables, it's a step function. It jumps at each possible value, and the jump height equals that value's probability. The CDF is always right continuous, always non-decreasing, goes to 0 at negative infinity, and reaches 1 at positive infinity. You can recover the PMF from the CDF, P at x equals f at x minus f, just before x. The expected value is the probability-weighted average of all possible values. For a fair die, E of x equals 1 times 1x plus 2 times 1x, all the way to 6 times 1x, giving 3.5. It's the long-run average. Roll a die infinitely many times, and the average converges to 3.5. 3 key properties of expectation. Linearity. E of x plus b equals a times e of x plus b. Additivity. E of x plus y always equals e of x plus e of y. No independence required. And for independent variables, e of xy equals e of x times e of y. Linearity is the workhorse of probability theory. Variance measures how spread out the values are around the mean. The definition is e of x minus e of x squared. But the computational formula is simpler. Var of x equals e of x squared minus e of x squared. Standard deviation is just the square root of variance, giving you spread in the same units as x. A uniform die has variance about 2.92. A die with only faces 1 and 6 has variance 6.25. More spread, higher variance. The Bernoulli distribution is the simplest. One trial, 2 outcomes. Success with probability p, failure with probability 1 minus p. Think of a single coin flip. The expected value is p, and the variance is p times 1 minus p. Every more complex discrete distribution builds on this foundation. Repeat that Bernoulli trial n times independently, and count the successes. That's the binomial distribution. The PMF uses combinations n choose k times p to the k times 1 minus p to the n minus k. The mean is np, the variance is n, p times 1 minus p. The bars form a bell shape centered at np. A binomial random variable is just the sum of n independent Bernoulli random variables. For rare events in a fixed interval, the Poisson distribution takes over. Accidents per day, calls per hour, typos per page. Its PMF is lambda to the k times e to the minus lambda over k factorial. Here's the signature property. Both the mean and variance equal lambda. When n is large and p is small, the binomial approximates the Poisson. That's the Poisson approximation in action. How many trials until your first success? That's the geometric distribution. Its PMF decreases exponentially. Each failure before the first success multiplies by 1 minus p. The expected number of trials is 1 over p. And here's the remarkable property, memorylessness. If you've already failed 5 times, the probability of succeeding on the next trial is exactly the same as when you started. Past failures don't change future odds. When sampling without replacement from a finite population, you need the hypergeometric distribution. Imagine a batch of n items with m defects. You draw n items. The PMF divides combinations of defects chosen. R combosenics 60 of. In Tiber bracons of good items chosen over all possible combinations. The mean is n times m over n. When the population n is much larger than the sample n, this approximates the binomial. These distributions are deeply connected. Bernoulli is binomial with n equals 1. The sum of independent binomials with the same p is binomial. When n is large and p is small, binomial approximates Poisson. The sum of independent Poisson, Poisson. And hypergeometric approaches binomial when the population dwarfs the sample size. The fundamental difference between discrete and continuous? Probability allocation. Discrete variables concentrate probability at individual points. Each point has positive probability mass, described by the PMF. Continuous variables spread probability across intervals. Any single point has probability 0. You need the PDF and integration to find probabilities. Countable versus uncountable. That's the dividing line. 3 things people commonly mix up. First, a random variable is a function from sample space to real numbers, not a regular variable that holds a fixed value. Second, PMF gives actual probabilities while PDF gives density. You integrate PDF to get probability. Third, independence implies uncorrelated, but uncorrelated does not imply independence. Independence means no relationship at all. Uncorrelated only means no linear relationship. Discrete random variables are everywhere. In statistics, they power hypothesis testing and parameter estimation. In machine learning, classification labels are discrete, and naive Bayes classifiers run on discrete probability. In engineering, reliability analysis counts system failures. In finance, risk models count defaults. In biology, population genetics tracks mutation counts. Here's your quick reference. Bernoulli mean p, variance p times 1 minus p. Binomial mean np, variance np times 1 minus p. PMF uses combinations. Poisson mean and variance both lambda. PMF has e to the minus lambda over k factorial. Geometric mean 1 over p memoryless property. PMF decreases exponentially. Hypergeometric mean n times m over n, sampling without replacement. And the general rules. Expectation is linear. Variance scales with the square of constants, and independence means variances add. Remember the universal properties. Expectation is always linear. E of x plus b plus c equals a e of x plus b e of y plus c. Variance of x plus b is a squared times var of x. And for independent variables, variances add, just like expectations always do. Discrete random variables turn uncertain outcomes into computable numbers. Master the PMF, expected value, and the 5 key distributions, and you have the foundation for all of probability theory.